Hello viewers, I am Kausalya. Today we are going to solve problem number 5, designing a lag lead compensator using Bode Plot, part 2. The problem is, consider the unity feedback system whose open loop transfer function is given. Design a lag lead compensator to meet the following specifications. So first one is velocity error constant, kV is equal to 80 and phase margin is greater than or equal to 35 degrees. So in part 1 we had designed the lag lead compensator and finally we had find out the transfer function of a compensator system. Right. Now we are going to draw the Bode plot for that compensator system. So step 11, Bode plot of compensator system. So this is the transfer function of the compensator system. Here in the transfer function we have replaced s as j omega. Right. So totally we are having how many terms? 1, 2, 3, 4, 5 and 6. So totally there will be six corner frequencies. So how to take corner frequencies? We have to take the reciprocal of the coefficient of omega. Right. So first we will start with this one, that is 1 divided by 2.5 and 1 divided by 0.22 and 1 divided by 35 and here 0.0154 and 1 divided by 0.33 and here 1 divided by 0.167. Right. So write down the values, first calculate the values and then arrange them in ascending order and then give the values of corner frequencies. Right. 1, 2, you see 1 is least 0.03 and the next higher value is 0.4 and to this the next higher value is 3, then 4.5, then 6 and 65. Right. So here we have to give the value of corner frequencies depending upon the ascending order. Right. So next we have to arrange them in a table. So our table as usual it has 4 columns. So terms, corner frequency, slope and change in slope. So the first place of the table will always contain constant with individual omega. So here the constant is 80 and the individual omega it lies in denominator. So 80 by j omega. So here first write 80 by j omega. Then the next thing is first write down the list of corner frequencies in ascending order, right? Starting from 0.03 to 65, right? Now 0.03 is contributed by which part? It is given by 1 divided by 1 plus j 35 omega, right? And again 0.4 corner frequency is given by this value. So 1 plus j 2.5, right? So accordingly just list out the terms here. Then the next thing is slope. So as we all know, omega in the denominator contributes a slope of minus 20 and omega in the denominator contributes minus 20 and omega in numerator contributes plus 20. Right. So here accordingly write down the values. Here omega is in denominator, so minus 20. Here again in denominator minus 20. Here it is in numerator plus 20. Again here omega denominator minus 20 and here in numerator plus 20 and again you see here in denominator so minus 20 and here in again denominator so minus 20. Right. Now we are going to calculate the change in slope. So here that is a constant term and individual omega will never contribute change in slope. Right. Then the next step is we have to move this minus 20 downwards and this minus 20 to the right hand side. So that gives minus 40. Likewise, we have to move this minus 40 downwards and we have to move this plus 20 here. So minus 40 plus 20 gives you minus 20. And the next step is again we have to move this minus 20 here and this minus 20 to the right hand side. So that gives minus 40. And the next thing is again we have to move this minus 40 downwards and this plus 20 to the right hand side. So minus 40 plus 20 gives you minus 20. So again this minus 20 and when you move this minus 20 that gives minus 40 and finally when you move this minus 40 downward and this minus 20 to the right hand side that gives a change of slope of minus 60. Right. Now we have to select a omega L whose value is less than omega C1 and omega H whose value is greater than omega C6, right? So here the value of omega L is 0.01 and here the omega H is 80, right? We can take any value as we wish here. And the next step is we are going to calculate the magnitude for different corner frequencies. So at omega equal to omega L, the value of magnitude is always contributed by constant with individual omega. So here we are having 80 by j omega and here the value of omega L is 0.01. So just substitute it over here and find out the answer, right? Again for at omega equal to omega C1, again we have to use this same formula and here the value of omega C1 is it is 0.03, right? So just substitute it over here and find out the magnitude. And the next step is at omega equal to omega C2. So there is always change in slope, right? So change in slope from omega C1 to omega C2, right? That is the formula. That is change of slope from omega C1 to omega C2 into log of omega C2 by omega C1, right, plus the previous value of A when omega equal to omega C1, right? So here from omega C1 to omega C2 the change of slope is minus 40 into log of omega C2 is 0.4 and omega C1 is 0.03 plus this is the value of A. At omega equal to omega C1 the value of A is 68. So just substitute it here, right? So the answer is 23 dB. Right, and again at omega equal to omega C3 again the same thing. Here the change of slope should be from omega C2 to omega C3 and again into log of omega C3 by omega C2, right? And the step goes like this, plus here the value of A when omega equal to omega C2 here, that is the previous value. So just substitute it over here and find out the magnitude, right? Likewise, we have to calculate the magnitude till omega equal to omega H, right? This is the same procedure as we followed in the previous case, okay? No changes in it. Just write down the formula, substitute the values and calculate the magnitude. That's it. And the next thing is we are proceeding to phase plot. So here how to calculate phase plot? Again tan inverse of imaginary coefficient divided by real term. So here in our transfer function, you see this is the given transfer function, right? So here we have to start from the numerator. So tan inverse of 2.5 omega divided by 1 and again plus tan inverse of 0.22 omega divided by 1. And now we are proceeding to the denominator part, so include a minus. And here this omega contributes minus 90 degree. So minus 90 minus tan inverse of 35 omega by 1 minus tan inverse of 0.0154 divided by 1 minus tan inverse of 0.33 omega by 1 and here again minus tan inverse of 0.167 omega by 1, right? Hope you people understand it, right? So just we are writing an expression, that is tan inverse of imaginary coefficient divided by real term. So this is what I had written here, right? These two are numerator terms and the remaining terms are denominator terms. So denominator terms comes with a minus sign. That's it, right? Now again the same procedure, just for different values of omega, calculate the values of phase angle, right? So here the different values of omega, it is mandatory, it should include all the values from omega C1 to omega C6. Apart from that you can include in between values and omega L and omega H, right? It depends. When you take more values of omega, you will be getting more accurate phase plot, right? So here when you substitute omega as 0.01 in this expression, what is the value of phase angle? Just write it over here. So likewise you just finish this table, right? Now we are going to draw this magnitude and phase plot in our semilog sheet. So here I have marked the points of phase plot and magnitude plot, right? So these are all the points I have marked. Let me join and show you. So this is the magnitude plot of the compensated system, and for each and every line it is mandatory to mention the slope, right? You see here minus 40 decibel per decade, and here minus 20, and here again minus 40, again minus 20, and minus 40, and finally we are having minus 60, right? Now let me join the phase plot. So finally we had drawn the magnitude plot, and this is your phase plot, okay? It goes like this. Phase plot of the compensated system. Now we have to check for the phase margin. So how to calculate the phase margin? As we all know, you see this is our magnitude plot, and this magnitude plot crosses this. This is our 0 dB line. So it crosses the 0 dB line at this point, right? So here at this point, from this point just draw a line downwards, right? I'm using a scale here. So when you draw a line downwards, it is meeting our phase plot at a particular point, right? So at this point exactly measure the phase angle over here, right? It comes around some 146, okay? Either it may be 146 or 144, okay? It doesn't make much difference. So here I am taking the value of 144, right? 144, 148, it may vary, plus or minus 2 degrees always accepted, right? So here now the value of our pi gc naught is 144 degree. Let us substitute this in our value, and again you have to write the scale, right? Everything is mandatory. So this is the plot of uncompensated system, even you can mention that too. This is an uncompensated system, and again this phase plot is for uncompensated system, right? Am I making the concept clear? Again we had drawn a new phase magnitude plot and a new phase plot, and we had calculated the phase margin. So here the formula is gamma naught is equal to 180 degree plus pi gc naught. So 180 minus pi gc naught, just now we had obtained from our Bode plot, it is 144 degree. Therefore the answer is 36 degrees. So what is the expected specification here? So here the phase margin is greater than or equal to 35 degrees. It is mentioned in the problem, and here we are getting the answer as 36 degrees. Therefore the design is acceptable. So here comes the end of the problem. If you have any doubt, let me know in the comment section. Thank you.